Hello, my name is Ajiboye Isaac, and today we want to discuss an important concept in statistics called the analysis of variance, commonly called ANOVA. Now, we want to consider two uses of ANOVA. The first case, we want to analyze the difference in the mean of treatment or effect of factors. And in the second case, we want to analyze the effect of one or more independent variable on dependent variable, predictor variable on response variable. That is, whether changes in the predictor variable causes changes in the main response. Now, these variables may either be quantitative or qualitative, as the case may be. Now, we'll consider two examples that can help us understand these two different uses. Example one, the data gives the number of hours of relief provided by 5 different brands of headache tablets administered to 25 subjects experiencing fever. So we want to perform analysis of variance and test the hypothesis at 5% level of significance that the mean number of hours of relief provided by these tablets is the same for all the 5 brands. Now consider the second example on my right. The income Y of an artist depends on the educational qualification X1 and years of experience X2. We might also want to test at 5% level of significance whether the change in income level can be explained by the changes in the educational qualification and years of experience of the artist. Now, the data provided, we can see some uniqueness in these different tables. We can see A, B, C, D, E treatment, and we can see X1, X2 predictors as against Y response variable. So the two examples will be approached differently, and the analysis of variance table is also presented differently. The example one, the structure of the analysis of variance is such that the source is identified as between, within, and total. And then we have sum of square for sum of squares for between, sum of squares within, and sum of square total. It is also important to point out that this sum of squares of between added to the sum of square within must give us the sum of square total, even in expression. Then the degrees of freedoms are also expressed, where k is the number of treatments and n is the total number of observation. We can then define the mean square error, or the mean squares, and then the F ratios. On the second example, example 2, we can see the structure of the ANOVA table. The sources are described as from regression, error, and total. And then we also have the degrees of freedom, the mean square, and the F ratio, where k is the number of parameter and n is the number of observation for the regression. So these are important structures, differences that we have to note. The technique of ANOVA consists of partitioning the total sum of squares into components that could be due to the difference in treatment of factors, in addition to the sum of squares of the error. And then, for instance, if there are Q factors, then the total sum of squares can be partitioned as SS total is equal to SS A, B to Q plus the SS error, where SSA is the sum of squares associated with factor A, SSB is the sum of squares associated with the factor B, and so on. Now, if the ANOVA involves only one factor, then it is called a one-way ANOVA. And if it involves two, then it is called two-way. And we can also have higher order ANOVA depending on the number of factors. I'll stop here so that we can therefore consider example 1, do the analysis of variance considering the example given to us. Thank you. In the next video. Welcome back. My name is Ajiboye Isaac, and now we'll proceed with the example 2. The income Y of an artist depends on the educational qualification X1 and years of experience X2. So we want to test at 5% level of significance whether the change in income level can be explained by the changes in the educational qualification and years of experience. The data is provided. we have column 1 for x1, column 2 for x2, and y column. We have different values there. So the solution is, we look at the table. It's a table of multiple linear regression, and the model for multiple linear regression is represented as y, the column matrix y equal to the product of the matrix x and matrix of the parameters plus error. Our hypothesis, we'll have our null hypothesis h naught defined as beta 1 is equal to beta 2 and is 0, signifying indicating no regression. Then our alternative hypothesis, denoted by h1, is saying that beta 1 is not equal to beta 2 and is not equal to 0. Now, it is a common practice to expand the table on my left for table of my right, so that we can obtain values that will be useful in obtaining our estimator. So we find the total of the x1, the total of the x2, the total of the y, then obtain a column for the product of the x1 and x2 and obtain the total, the product of the x1 and y, similarly the product of the x2 and y, and that we can get our total from there. So from the table, we can then obtain our x prime x, and the matrix for our x prime x is already expressed, where we have the first entry as a number of observation, the sum of x1, the sum of x2. If you look at, you see the first row and the first column have the same entries, and so on. So we already have the totals. These totals are now then imputed to form our x prime x matrix. After that, we obtain the inverse of the matrix, and then also obtain our x prime y, which can be expressed as the formulas: the sum of y, the sum of x1 and y, product of x1 and y, x2 and y. And so our estimator, beta hat, is the product of the inverse of the x prime x and x prime y. That gives us that column matrix we have there. So we can therefore obtain our sum of square total, which is the y prime y minus the square of the sum of y over the total number of observation. That will give us 421 minus 351.125, which is equivalent to 69.875. Similarly, the sum of square regression is the transpose of the beta obtained times the product of the x prime y minus the square of the sum of y over the total number of observation. That will give us 408.69 minus 351.125, which will eventually give us 57.561. It's a common practice to obtain our sum of square error by subtracting the sum of square regression from the sum of square total. And that will give us 69.875 minus 57.561 to give us 12.314. So we can then fill in our ANOVA table that way and then obtain our F ratio. So once we obtain our F ratio from the ANOVA table, the next thing would be to obtain our F table. Go to the table of the F distribution, check the F at 0.05 level of significance, 2 and 5 degrees of freedom respectively. So the value is giving us 5.71. Then we compare this value with the value we obtain for our F ratio. So our conclusion, since our F statistics, which is equivalent to 11.685, is greater than the F table, the value from the table, which is 5.79, we reject the null hypothesis that there is no regression, and therefore conclude that there is evidence that the predictors jointly explain variation in our y. So how much of the variation is explained by y? that we can get from the coefficient of determination. And coefficient of determination, R square, is the ratio of the sum of square regression to that of the sum of square total. Then we'll take the 100% of it. So that gives us 57.561 over 69.875 times 100%, which will give us 82.38. And that implies that 82% of the variation in Y is explained by the predictors, which is indicating a good regression model for the data, which indicates that our regression model is good for our data. I'll stop here. In our consequent video, would also look at other examples.